3 more practice questions. So relating force and motion, I'm trying to give you a variety of questions to work through. I hope you're seeing that the approach is similar, but the reasoning through it is very dependent upon the question itself. So here we go. Please pause and read through this question. Decide your answer and then check your answer. All right, so we actually have these 2 cases that we're looking at. The question overall wants us to know which one has a greater normal force. Please do not assume N equals mg in all problems. We've seen many problems where that is a true statement, but this is not one of them. So C is definitely not the answer here, and I'm going to reason through that for you. Hopefully we can follow along. So in terms of drawing a free body diagram, that's always my go-to. Draw a free body diagram. We need to decide what we're drawing the free body diagram for. Do I want to draw the free body diagram on the physics student or on the sled that has the kid on it? Well, the normal force is, well, the wording is implying essentially we want the normal force we want to compare them on the sled, the child sitting on the sled. Either way, my free body diagram, the dot I am drawing, is going to represent the child on the sled. In either case, we're going to have the force of gravity or weight pointing downwards. I'm not going to be careful drawing the length of my vectors. I'm just really going to account for directions mostly, and then we will walk through this. So mg, this force of gravity or weight, accounts for the pull of the earth, that gravitational attraction of the child on the sled towards the center of the earth. Any other forces are contact forces. We know the sled is in contact with the snow, the ground. We know there has to be a normal force pointing upwards in either case, simply because the sled is on the ground is a surface, surfaces push with a force that points perpendicular to the surface. The other potential force we can look at is friction with the ground. I assume a sled on snow would have very little friction, but if it did have even just a little friction, we know the friction would oppose the motion in either case. So I'm going to go ahead and just draw a little friction here in both cases. It's specifically kinetic friction because the sled is sliding on the snow, on the surface. Okay, we have one more contact force to account for. In case 1, the student is pushing on the child's back, which in turn is giving the child's sled combination a force. So I'm going to come draw that. The force is down at an angle, and they've labeled the angle up here. I can draw it in my picture down here. That angle is with respect to the horizontal. So the push that the student is applying to this child has X component and Y component. In case 2, the student is not directly in contact with the student. There's some sort of rope tied. So there's a tension pulling up and to the right, but we're told that that force of tension is however hard the student is pulling, So I'm still going to label it F to mean the same magnitude, and then theta. So both case 1 and case 2, normal force, pushing or pulling force at the same angle, friction, gravity. This question is specifically wanting us to compare these normal forces. Since the normal force is simply in the y direction, let's just talk about net force y. We know any net force in the y direction will lead to an acceleration in the y direction. So whether we write this equation as acceleration in the y direction is the net force over the mass, or down here I've essentially solved for the net force in the y direction is mass times acceleration. Either starting point is fine. It's the same equation, just solved symbolically for force versus acceleration. Coming back to the problem. So this, in either case, that push or pull is going to make the child continue to move horizontally along the snow. So the acceleration specifically up and down in the y direction is 0. Because again, if there's an acceleration in the y direction, that means the velocity has to be changing in the y direction. So the child would actually have to be lifting off the snow, flying into the air, or sinking deeper and deeper into the snow somehow. So there is no acceleration in the y direction, meaning the net force needs to be 0 in the y direction. So we need to balance the forces. Balance y direction forces is what we're looking at. So ignore case 2 for just a second. Let's look at case 1. In case 1, we have this force, this pushing force that has an x component and a y component. In terms of balancing the y forces, we would say that this upward normal force, well, Fy's down, mg's down, so the normal force is the only upward force, so that needs to be counteracting mg down and Fy down, the y component of this pushing force. So this is essentially telling us the ground has to push up harder than the weight. So this is the weight of the sled and kid together. But the ground also has to push up to counteract the downward push. This guy. Jumping to case 2, this force has x and y components as well. But this y component points up. So when we're balancing the forces, because there's no acceleration, we can say that the normal force and the y component of that pulling force are working together in the upward direction. And they are balancing out mg that's in the negative y direction. So the upward pull is helping the ground counteract the weight of the child's sled system. If we solve for the normal force here, we find that the normal force will equal mg minus that y component. So the y component of the force has the same numerical value in both cases, but because of it being down in one case and up in the other, that affects the balance of the forces in the y direction and in turn affects the normal force. So coming back to the problem, we want to know in which case is the normal force greater. Well, case 1. Case 1, the ground has to counteract both weight and the downward push. The normal force in case 2 will be smaller, simply because of how that pulling force is applied.